So we're going to take this equation, Gauss's law, and look at some applications to Gauss's law. And so we go to apply Gauss's law. There's a few steps that we need to go through first. The one thing to point out is that Gauss's law works very well when there's a certain symmetrical distribution of charges. So the first step is to choose a Gaussian surface that's appropriate to the situation. We want to have a closed surface that I can close charges. Surfaces that may be appropriate for that situation. If you have something like a sphere or ball of charge, maybe it makes sense to have a surface which is spherical. If you have something like a long straight wire, maybe something that is cylindrical makes sense. If you have something that is a flat sheet, maybe a cube makes sense. We'll look at some situations and start to figure out that there are really, I think, of three different symmetries that we come across over and over again. One of them is a spherical symmetry, one of them is a cylindrical symmetry, and one of them is a planar symmetry. Then we set up the equation for Gauss's law. The one thing that I pointed out about that equation is that on the right-hand side, that surface integral with the dA, the surface integral of dA, if you've defined your system right, just becomes the surface area of the surface. So you're defining a surface, so the electric field is always perpendicular to that surface. That's how you make that trick work. On the Q enclosed side, that actually may require an integral, even though it looks like it is just a number divided by a number. Then we can solve out for E, and we're done. So we'll do some applications in this lesson. I'll talk about more applications or more situations that you come across when we go in class and look at Gauss's law in class. So the very first situation that I want to do is, say we have a solid conducting sphere that has a charge plus Q that is uniformly distributed on its surface. The one thing to point out about a solid conductor is that the charge has to be uniformly distributed on the surface because the charge will try to spread out in a way to get as far away from each other as possible. The distribution of charges which makes them be as far away from each other as possible happens to be, well, outside of the surface of the object. So we want to figure out if this sphere has a radius of r, capital R, what is the electric field both inside and outside of the sphere? So if we go inside the sphere, so little r is equal to something less than r. So basically I'm choosing a Gaussian surface which looks like a sphere. It actually models the shape of the object I have. My Gaussian surface is centered at the center of your solid conducting sphere. So we look at the amount of charge that's going to be enclosed here. The amount of charge that's going to be enclosed here, well, first of all, the surface area of a sphere is just 4 pi r squared. That's what's going to happen to the right-hand side, just E times the surface area of a sphere. Well, the amount of charge that I've enclosed by that red sphere is actually 0. All the charge is on the outside of the sphere. What that means is, for a conductor, the electric field inside the conductor happens to be 0. Now what if I looked at outside the sphere, something where my Gaussian surface, the radius is bigger than the radius r? Surface area of the sphere hasn't changed. That step looks exactly the same. The one thing to point out is that the Q enclosed by this surface happens to be the total charge of the sphere itself, Q. If we solve out for E, we get Q over 4 pi epsilon naught r squared. That looks a lot like Coulomb's law for a point charge at the center of the sphere. And in fact, if you're sitting outside the sphere, you would not know whether you're dealing with a conductor that has a radius big R. You would not know whether you're dealing with an insulator with a radius big R, as we'll see in the next lesson, or a point charge at the very center. All three of those scenarios would look exactly the same to you if you're on this red sphere. So the next one, I wanted to take a solid insulating sphere, and let's say we took that charge positive Q, and it's uniformly distributed throughout the sphere. So it makes an insulator different than a conductor. As an insulator, it can have charges distributed throughout the inside of the surface, or throughout the inside of the substance as well as the outside of the substance. If we look outside of the sphere, what we get is a set of equations that looks almost exactly identical to the conducting sphere outside the sphere. Q enclosed over epsilon naught equals the surface integral of E dot dA. Surface integral of dA is equal to 4 pi r squared. Charge enclosed is still Q. And in fact, we get the same exact formula. So whether it's an insulating sphere or conducting sphere, if I'm outside the sphere, the electric field's going to look exactly the same. But here's where things start to get a little funky. What if I'm inside the sphere? So that statement holds true up to here, but now I run into some troubles calculating Q enclosed. Now I said sometimes on the Q enclosed part you need to use an integral. This would be one of those times. I need to figure that out. The way to figure that out is to say Q enclosed is equal to the integral of dq. Well, I need to define what dq looks like. The way I would define dq is whatever the density of charges times dv. So I need to figure out dv, basically what's the volume of, well, you can think of it as a thin spherical shell inside there. We can find rho pretty easily. Total charge divided by the volume of the sphere. The way I define dv is 4 pi r squared, the area of that surface, times dr, the thickness of that surface. So you can think of this like, dv like the thin candy shell on the outside of a spherical shaped candy. What is the volume of that thin candy shell? This is the way you could calculate it. So we plug those in to find Q enclosed. I'm going to integrate this from 0 to r because the area of the volume that's enclosed in this sphere is from little r equals 0 to r. And if we actually solve this out, a bunch of things start to cancel out. Then we can integrate r squared, which becomes r cubed over 3. And so we get the Q enclosed is really Q times little r cubed divided by big R cubed. Well, I can now plug that in there to my formula and now divide everything by 4 pi r squared. And what I get is a very interesting relationship. What it suggests is that the electric field increases in a linear fashion as I go from the center of the circle to the outside of the circle. It also suggests if r, the little r, is equal to big R, I get something that looks like, oh, I'm outside the sphere. So that's a couple of examples of spherical symmetry. We'll look at a few other examples. One of the other examples that I like to look at is a sphere with a spherical shell around it. That's actually a fairly fascinating situation to look at, and we'll look at that one in class. So let's find the density of, or let's find the electric field created by an infinitely long line of charge with a linear charge density of lambda. Now I've actually already done this one when we went and looked at, say, a line of charge and said, what if this line is infinitely long, what happens? The type of Gaussian surface which makes sense in this case is a cylinder. The reason why is we can define the surface of the cylinder around this wire so that the electric field is perpendicular and the same strength at all points of the surface. I'm going to call the cylinder, give it a length L and a radius R. So I'm going to apply Gauss's law. The one thing to point out is through both ends of the cylinder there's no flux because electric field is parallel to that surface. And so all the flux happens to be around the side of the cylinder. So we want to figure out the area of, well, the side of a cylinder. Well, imagine taking a cylinder, cutting it down the line and spreading it out. What would you get as the area? Well, you get the circumference, 2 pi r, times the length L. Now it's worth pointing out the charge enclosed inside the surface is just going to be lambda times L. A linear charge density is charge per unit of length. And once I've done this, I can solve it out and get the electric field is just lambda over 2 pi epsilon naught times r. I will challenge you to go back a couple of lessons and look at problem J3 and look at the solution to problem J3 when we assumed that it was an infinitely long line. And you have the same exact solution. This one's just, I don't know, about 5 times easier to get to the solution than doing integration for a line of charge. The last one that I want to look at is the electric field caused by a uniform infinite plane of charge with an areal charge density of sigma. You'll see with charge densities we almost always use lambda to talk about a linear density, charge per unit of length, sigma to talk about an areal density, charge per unit of area, and rho to talk about a volume density, charge per unit of volume. So we're going to still use Gauss' law. Q enclosed equals the surface integral of E dot dA. In this case, I've used another cylindrical surface, and I've stuck that cylindrical surface straight through the plane. So half of the cylinder is on one side and the other half of the cylinder is on the other side. And so the end of the cylinder is a distance, I think I'm going to use a distance r away from the plane. So the one thing to point out about this is that the two areas that matter where there's flux are the two ends of the cylinder. There's no flux to the center of the cylinder. And so the area of one end of the cylinder is pi r squared. And there are two of them, so 2 pi r squared is what we get. Now, it's worth pointing out that when we actually solve this out, we get sigma over 2 epsilon naught equals the electric field. Now, that is to work out, we've also done this solution, or you can get this solution out of a previous problem. If you go back to the problem where we talked about a uniform disk of charge, if you make the size of the disk, the radius of the disk, much bigger than the distance you are away from the disk, you actually end up with the same solution when you work it out. What this would also suggest is it doesn't matter how far away from this plane is, my electric field is constant, which is actually pretty darn cool if you think about it. So let's get a couple quick applications of Gauss' law. Like I said, we'll go over some other applications in class and look at how we can modify some of these situations to deal with other types of situations. Some other ones that are pretty cool to do, like I said, the sphere with a spherical shell outside of it. Also, you can do something like a cylinder of charge, or a cylinder with a cylindrical shell outside of it, what I would call a coaxial cable. Those are also kind of fun to play around with. So we'll look at some of these other scenarios in class and kind of talk through how would we set up these types of problems and how will we do these types of problems. I think spending some time on Gauss' law is actually pretty important. If you go back and look at the AP exam, what you find is that Gauss' law shows up over and over and over and over again. It's probably one of the most reliable types of problems to show up on the AP exam in the spring.